Alright, this video is going to be on rates of change. And we've already talked about most of these things before, and so this is going to feel a little bit like a review of kind of putting everything together and making sure that it all makes sense. So, in the past, in our old math classes, we looked at average rate of change. And when we looked at this really meant old school slope, right? So we called that M, and we were looking for that in the past. We also might call this the slope of a secant line. And the slope of a secant line just means you're taking the slope through 2 points on a curve. So secant lines cut through curves. The third thing about the average rate of change is that it's over an interval. So it's from one number to another number. And we talked about this in the past. We said this is rise over run, which is the same as delta y divided by delta x. So that's your change in your y values divided by your change in your x values. So average rate of change is what we're very comfortable with. We've done it a lot in the past. Now in calculus, we're starting to get into more advanced mathematics. So now we're talking about instantaneous rate of change. And so that's different because now we're not dealing with the old school slope. Now we're talking about the derivative. And we're not talking about the slope of a secant line, we're talking about the slope of a tangent line. Which is 1 point on the curve. So that means that the tangent line does not cut into the curve, it literally sits on the edge of the curve. Third, instead of looking at over an interval of numbers, we're going to say at a specific instant. And then also, instead of having delta y divided by delta x equals the change in the 2 points, we're going to say that the derivative is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we have a different way of finding it. So again, none of that's new. All of that's old news. I just wanted you guys to have a really good, clear picture of what the two different things are talking about. Alright, so we're going to go ahead and just do a couple examples, making sure that we understand this new type of rate of change. So we're going to say the total household energy consumption, which is going to be described as E of t, in Germany in year t, is going to be described using this table, and we're going to go ahead and copy the table down. So we're going to have the year that we're talking about, and then how much energy consumption we have. And so the units for the consumption are 10 to the 6th. I think kilowatt hours is what that is. I don't recognize that unit. If I'm wrong, tell me so I can fix it. So, and the years we're going to look at are 2002 through 2006. And we're going to have 136.5. 139.1, 140.4, 141.3, 141.5. Okay, so what we want to do is find an estimation for E prime of 2003. And the reason we have to find an estimation is because we don't have an equation. So we can only find the exact number if we had an equation to work with. We don't. So we're going to find an estimation of what the derivative is at 2003. And we also want to interpret that answer. So this has to do with the rate of change, and it's the rate of change in an instant. So what we're saying is in 2003, the energy consumption in Germany is increasing or decreasing at a specific rate for that year. So we're not saying over a period of time, we're saying at that year there's a specific rate of change happening. So I'm going to go ahead and write out this sentence of what this actually means, and then we can do some math to find it. So in 2003, energy consumption in Germany is increasing or decreasing. I'm not sure yet. I'm going to figure it out when I have a positive or a negative answer. At a rate of something kilowatt hours per year. Okay, so that's the instantaneous rate of change I'm trying to find. And to do that, we're going to go ahead and use our old school slope formula. And so I'm going to say that the instantaneous slope is approximately this number because this is not an accurate number whatsoever. So for us to get a good guess for 2003, it makes a lot of sense for us to use from 2002 to 2004. If I guess from 2003 to 2004, don't draw this on your paper. But let's say we have like a curve that goes like this, and this is the slope. That's the point we're trying to find the slope of. If you pick the point next to it and then find the slope right there, that might not be as accurate as if you took this point over here and found the slope over there, if that makes sense. So that's kind of what we're doing right now, is we're going to say, all right, to find the instantaneous slope at 2003, I'm just going to use 2004 and 2002 because they're on either side. And that will probably be more accurate than if I use 2003 as part of my answer. So I'm going to say the change in the y values, that's 140.4 minus 136.5, divided by the change in my x values. And so I'm saying this is approximately the slope. It's about 1.95, and then I have to remember my units. That's times 10 to the 6th kilowatt hours per year. And so this is a positive number, so we're going to go back and say that the consumption is increasing over time. And you can see that it's increasing. I guess we could have written that before. And that was 1.95 times 10 to the 6th. All right, we're going to do one more example, just in using what rate of change might mean in the context of a problem that seems a little bit more calculus appropriate. So we're going to say let A equals pi r squared, and hopefully you're noticing that's the area of a circle. And we're going to say B the area of a circle. With radius r. And that language right there, let some equation be the area of a circle with radius r, that's very common, like kind of formal math language, just kind of spelling out exactly what that equation means. So the first thing that we're going to do with this equation is we're going to compute dA dr, and I'll write off what that means in a second, at r equals 2 and r equals 5. And underneath, we'll go ahead and write down what that means. dA dr is the change in area with respect to the change in radius. So it's basically saying, as the radius changes, this is what's happening to the area. And so this is a rate of change. It's an instantaneous rate of change at r equals 2 and r equals 5. So for all intents and purposes, we are saying that dA dr is the same as the derivative of the area. Okay? because we're talking about a rate of change. We're talking about the rate that the area is changing with respect to how the radius is changing. All right, so that's the first question. The second question we're going to answer is why is dAdr getting bigger, going to be bigger when r is 5 than when r is 2? And that's, if you think about it, you can probably figure it out. But we're going to go ahead and look at that second. So first, let's do some math here. I'm going to go ahead and find the derivative. So I'm saying the derivative of this, and now we can use our little shortcuts. So I'm going to say 2 pi times r to the first. And you don't really need that little 1 there. You can leave that out. And this is the same as dA dr. And then we're going to go ahead and say, I'm going to evaluate dA dr at 2. So this is notation. This is just saying I'm going to evaluate this, the answer that I got, at 2. And so that gives me 2 pi multiplied by 2, which gives me 4 pi. Next, I'm going to go ahead and evaluate the same thing at 5 for a radius of 5. And that gives me 10 pi. So if you can see this, the derivative of area is perimeter. That's what this is. That's the perimeter formula. Okay, so now we're asking ourselves the question, why is dA dr larger at r equals 5? So if you understand what dAdr means, it means the change in area with respect to the change in radius. The value is bigger when the radius is 5 because an increased radius is going to increase the overall area. Okay? So the value is bigger. I'm going to say dA dr is larger when r equals 5 because as the area increases, or as the radius increases, the area of the circle increases.